I was planning to go until to do the tensor PCA and the low-rank matrices with sparse factors with the S in the second part, but okay, I did the tensor in the first part. So basically, we started talking about rank 1 models with structures, and then we tried to extend it to higher order tensors, so to get the order larger than 2. And the next generalization I'm going to talk about is when the rank of the unknown gets larger than 1. We are not going exactly to give the same kind of guarantees and look at the problem in the same way, but again, we are interested in statistical threshold and also to see what we can do computationally. So this part is joint work with my colleagues in France, Guillaume Obozinski and Jean-Philippe Vert. So as I said, the goal in all these problems we considered is to write the unknown as a small as a linear combination of a small number of outer products of vectors. So what does it mean? It means that, for instance, if V is V0 denotes the unknown, we want, or V0, V1 until VR denote the unknowns. We want to write denote the signal. We want to write the unknown, which is a linear combination of V0, V0 transpose, or this type of elements with some specific structure on V that we denoted by a cone constraint. So the way to build elements that have that contain several a linear combination of these small atoms is to consider the convex hulls of those set of interesting elements. So by building this kind of objects that we call convex envelope or lanterns. So the way it works, we have a set of elements that is the set of elements of interest. And what we associate to this set of elements, to the convex hull of this set of elements, is a function that is the gauge of this convex hull. So back in 2012, based on this paper, people decided to call these kind of convex objects atomic norms. And these are actually going to be norms in case the set of atoms is centrally symmetric. And so I'm going to give some examples. But in terms of this set of atoms, the atomic norm can be formulated as the gauge of the convex hull of the set of atoms. So it's a function whose unit pole. Yes, please.
This construction is from the literature on nonlinear approximation in the early 1990s.
Yeah, the vocabulary gauge comes from the. The atoms, they use the term atomic? Yeah. Okay, I had seen it in signal processing, like they were calling the wavelets in which basis they wanted to expand the signal as atomic. And I had seen the word gauge in Rockefeller.
Yeah, so it's,
okay. Okay. So what was the reference you mentioned? Okay. Okay, good to know.
The idea that you want to use these things on sparse approximation to express the complexity of an object dates back a long way. In fact, they developed approximation theorems in terms of exactly this quantity. And so,
okay.
The idea that this is somehow, 2 or 3 or 4 years old is
okay, thank you. So this gives us a variational expression of the function, which is the infimum over the set of linear combinations. So here CA, this is a mistake. This CA is a positive number, and so if the unknown, if the input vector is expressed, we take the infimum over all the convex combination of the elements in the atom set, And we define the norm as being the sum of the coefficients of the convex combination. So the infimum over all this set of real numbers is going to give us the value of the norm. And the nice thing about it is that the dual can be expressed very easily. Is the supremum over all the set of atoms of the inner product of the atom by the input element. So the nice thing here is that we see a connection with what we had before. This problem is similar so this optimization problem is similar to the structured PCA problem we had before. If the set of atoms is the intersection of the cone with the unit sphere, so here outer product with itself. And so here we see that the value of the problem structured cone constrained PCA is the value of the dual norm of the atomic norm, which is associated with this set of atoms. And the primal norm is what is named the nuclear norm in the general use of this vocabulary of nuclear norm, which, okay, so on this one, the oldest reference I know is by Jameson, the book of Jameson, but I think yesterday you mentioned, okay, 1940. But Jameson's book is 83. 83, okay, so, but, okay, anyway. So two examples of this kind of norms that are very popular are the L1 norms. So if you take the set of atoms to be the indicator of different entries of the, okay, or if you take the canonical basis, plus or minus the canonical basis, and you write the gauge associated to the convex hull of this, you get this nice diamond that is the norm, the unit norm of the L1 norm. And the same way, if you take the vectors, which can be written as AB transpose with A unit norm vector in our N1 and B a unit norm vector in R N2, and you built the atomic norm associated with this set of atoms, which is centrally symmetric, you get a norm which is the trace norm or the sum of the singular values of the matrix. So one good thing, there are several good things about these norms, which is, for instance, if you know that you want to estimate an element which can be written as a linear combination of a few atoms, this is the tightest convex relaxation to the problem. And on the algorithmic side, there is one algorithmic scheme that is built kind of by using directly this kind of structures, which is named the conditional gradient. So it's also an algorithm which I think dates back to the 60s or 70s, but which had a renewal recently due to its use for matrix completion problems. So I'll explain how the algorithm works, and it will give you a good intuition why people who were working on matrix completion started to use that algorithm, and it gave good results. So the algorithm is taking, so it's trying to minimize a smooth and convex function subject to the constraint that x should belong to a convex set, which is the convex hull of the set of atoms. So scaled with a factor, which is the value of the norm. The algorithm is an iterative algorithm, which at each step takes a convex combination of the last element with a new atom that is built by taking the vector that is the closest possible to minus gradient. So if you solve this problem, if you minimize over the set of atoms, and since this set is convex and this objective function is a linear approximation to the gradient, the value of this problem, so x belonging to the convex hull of the set of atoms, is going to be the same as the problem subject to x belonging to the set of atoms itself. And this is due to the fact that we are doing a linear approximation, and the set is the convex hull of that set of atoms. So, so at each step, you're building a linear combination of the previous element with a new atom, and it's known that after t steps, you are a factor of something over t away from the optimum, and this something depends on your initial point. So the convergence of the algorithm is pretty slow, but the good thing is that if you have a good solver for this step, you get an algorithm that is probably going to converge to the solution. And so the reason why this algorithm got popular when working on matrix completion was that rather than having to compute the full SVD of the matrix at each step of your iterative algorithm, so if you use a prox gradient algorithm, or it's also called a subgradient algorithm, at each step of your algorithm, you take a gradient step on the loss function, and then you have to compute the proximal. And the proximal, the way it's computed, you need to compute the full SVD of your matrix and shrink the singular values that are smaller than some threshold value. So that step is prohibitive. It requires a cubic number of flops, whereas this step, in case of matrix completion, just requires to compute the leading singular vectors of a matrix, which requires n squared log n, and it's very nicely parallelizable. So if you have a multi-core machine, it can go pretty fast. So based on these ideas, we started to think about the sparse PCA problem and related problems which involve factorizing a matrix with sparse factors. And the way we tackled the problem, we said that, okay, so let's say that we fix the number of non-zero elements on each of the factors of x. So x is written as a linear combination of r factors. Each of the factors has a specified number of non-zero elements. So by formulating the problem like this, so we call k and q the number of non-zeros in each of the factors a and b. By formulating the problem like this, we are able to write the sparse PCA problem for the sparse PCA problem for rank larger than 1 as an optimization problem. The way the problem was tackled before was by a methodology that people usually call deflation. So they basically compute one factor, they either subtract that factor or do some kind of projection. But it was there were several methods that were tried in the literature, and none of them had an optimization interpretation, and it was not. We'll see that our method is doing better on benchmarks and in several aspects. And so also with this construction that we have, we can have interpretation on each of the factors separately, and also we'll prove that by fixing the size of the support of each of the elements, we are capable of building a norm which has probably better statistical performance than the previous norms that existed and that were used for the problem. And this will prove that this is the statistical rates we obtain are near optimal. So here, before building the set of atoms on which, using which we build this atomic norm, we introduce the notation A n index j. So n is the size of the vector space, and j is an integer, which is going to denote an upper bound on the number of non-zeros in the factor. So the set A and J is the set of vectors which have L2 norm equal to 1. So this is a subset of the sphere. It's the intersection of the sphere with a non-convex cone, which is the union of several J-dimensional spaces. And the using this, we introduce the outer product of the sets A n1k and A n2q to build the set of atoms we are looking at, and we introduce what we call the KQ rank of a matrix. So it's a specification of the rank. So the rank is the smallest number of factors A and B you need to write your matrix as the linear combination of AB transpose. Here we add the constraint that the factors A and B should be of sparsity K and Q. So this way we are building an index which has the same flavor as the rank or the L0, but with the difference that we specified that the factors should have the target sparsity. So this also can be written as the minimizer of this problem. And by looking at this, we can immediately see that the KQ rank is finite and is actually bounded by N1 times N2. So the norm we are going to build is the same thing as the L1 norm is to the L0 index, or the same thing as the trace norm is to the rank. So this way we are saying that our norm is going to be the tightest convex relaxation of the KQ rank over the, if you make the relaxation over the operator norm ball. So the norm is defined by using the set of atoms that is the outer product of these two sets I discussed about right before, and it can be written as the solution to an optimization problem. So we have a variational expression for this norm, which is the minimum L1 norm of the vector C. So the vector C here has maximum length N1 times N2 of this linear combination, where the elements A1 and B1 have sparsity K and Q respectively. So this gives us a norm which we cannot compute numerically. So, but we have a nice expression of it, and we know basic things like the norm is always going to be lower bounded by the trace norm and upper bounded by the L1 norm. And we know that the L1 norm can be written as this norm with indices 1 and 1, and the trace norm is the value of this norm for values of the, so by removing the bounds we have on the sparsity index, so by putting K equals N1 and Q equals N2. We have also a formulation for the dual of this norm that we know since we built the norm as being an atomic norm. So the dual norm is going to be given by the maximum over all the supports of size K and supports J of size Q of the operator norms of submatrices which are non-zero over these supports. So sorry. This is a submatrix of our matrix, which has indices belonging to I Cartesian product with J. And it's the maximum of the operator norms of these. And using this, again, we can write the value of the norm as the solution of another optimization problem, which is the infimum of the sums of trace norms of matrices A, I, J. Here, these are not submatrices, but these are matrices which have supports included in the set I cross J, such that the sum of the AIJs equals the matrix Z. Okay? So the value of the norm is the infimum of the sum of trace norms of these small matrices. To get an intuition of how this norm looks like, we can plot it in the vector case. In case one of the factors is flat, so when N2 equals 1 and Q equals 1, this norm gives us a norm that is named as that is known as the K support norm, or it's the overlap group lasso, where the groups are we consider all the groups of size K. So this has this can be represented as the convex hull of the union of three disks. So here are the three disks, and which is the set of atoms, the set of elements of sparsity 2. And if we take the convex hull of this, we get this norm that is the unit ball of the 2 support norm in R3. So for analyzing this norm, we we can use again the statistical dimension, and we are going to compute it at we are going to compute the statistical dimension of the tangent cone to the norm at a point which is the point of interest. So typically we are going to look at the atoms and look at what is the value of the statistical dimension, so the expected value of the square of the norm of the like L2 norm of the projection of a Gaussian vector over this tangent cone. So here is the point in the space, which is typically going to be one atom or a linear combination of a few atoms. This is the tangent hull of the cone, and we project the vector G onto the tangent cone, and we integrated to get the value of the statistical dimension. What we know from previous work is that if we get a small value of the statistical dimension, the number of observations you need to get exact recovery in compressed sensing kind of problems is going to scale with the dimension of the problem times the statistical dimension with these normalizations I used. And we already, Holger already discussed it yesterday, and yeah, today it's a standard metric for thinking about this kind of inverse problems. So what we obtained, the result we obtained was that the statistical dimension, so here I'm considering symmetric matrices just to simplify notations. The statistical dimension times the dimension of the space is bounded by a term which is of order of k log n. So the standard norms, if you take, for instance, the L1 norm, and you compute the statistical dimension on an atom, which has sparsity k times k, so it's going to have a sparsity k square. We are going to obtain a statistical dimension that is of order k squared times log n over k. And if you take the trace norm, the statistical dimension on an atom of this norm is going to be of the order of of n, which is the rank of the atom. So the atoms are rank 1 elements, and the statistical dimension on an atom of the trace norm is going to be n. Here we get a statistical dimension of order of k log n, which is way smaller than both these two rival norms, and also smaller than any linear combination of the trace norm and L1 norm, which is the standard candidate to estimate matrices which are sparse and low rank. There is a coefficient behind this k log n, which we denoted by gamma. It's the strength of the atom. So if A transpose is the atom on which we are computing the statistical dimension, this strength coefficient gamma is k times the minimum of AI squares, where I is in the support of A. So this coefficient is between 0 and 1, and it's going to get small when the atom gets close to, when the smallest element of the atom gets small. So basically what we are stating is that if the atom is the vector with all entries equal in magnitude, equal to 1 over square root of k, we have the best statistical dimension. So it's the cases, the most favorable cases for estimating these vectors. And the less favorable cases are cases where some of the coefficients are getting small. And this is also known in the analysis of the lasso and of vector problems. So it was intuitive to find a parameter like this, and the only thing we don't understand is why we have a square on this gamma here, and if we look at the vector case, we don't have the gamma square in the first term, so we hope to be able to remove this square here soon. And what the representation I have here is the set of atoms for 3 norms. So in green, I have the set of atoms of the L1 norm and also the edges. And here in blue, we have the set of atoms of the K-support norm, which was the norm that has this green ball here as the unit ball. And in red, it's the atoms and edges associated to those atoms of the norm that we called kappa k. It's known as the Kifan K norm in case of matrices. In case of vectors, it's a polyhedral norm which has those vectors with equal in magnitude entries on the supports of size k as atoms. So these points are the most favorable points, and as we see on the L1 norm, even points that are getting close to this one are going to have the same tangent cone, whereas for the K-support norm and also for the outer product of K-support norm and Q-support norm, which builds our norm, these are the less favorable points. So as I said, we are gaining a factor compared to the trace norm and compared to the L1 norm when we compute the statistical dimension of this norm, and we cannot hope to do better than k over n, since we know that if the support is specified in advance, we are going to get the norm that is the best to estimate the unknown matrix is the trace norm of that submatrix, which has statistical dimension k over n. So we know that we cannot do better than k over n. And this factor log n is there also tightly in case where we vectorize the norm and we look at the K-support norms statistical dimensions. So we know that we don't hope to get rid of the log factor. It has a combinatorial reason to be there, but we have a lower bound which is only of the order of k over n. We don't have a k over n times log n lower bound. The interesting thing here in this table is that when we compare this norm with the equivalent norm in the vector setting, in the matrix setting we are gaining a factor compared to the rivals, whereas in the vector setting the K-support norm has the same statistical dimension as the L1 norm has. So there is a gain in the vector in the matrix case of building this atomic norm, which is built by using the fact that we knew the size of the support that we don't gain in the vector case. So on the algorithmic side, we know that finding solving the problem for rank equal to 1 is a hard problem. Like the worst case complexity of the problem is non-polynomial. But there are some routines which are similar to power iteration. Like if you do power iteration and you truncate the vector at each iteration, you converge to a vector which is a good candidate for a new for a set of support that can be included in the active set. If we want to solve the optimization problem of minimizing a convex loss plus the KQ trace norm by using a coordinate descent or active set kind of algorithm. So the algorithm that we have works as follows. At each step of the algorithm, we have a matrix that is written as the linear combination of a small number of matrices of which have support included in sets of specified size k and q. At each step, we try to find a new candidate set for updating the set of so-called coordinates of this coordinate descent algorithm. This set of coordinates is the set of all matrices whose support is of size k by q. Okay, so at each iteration of the algorithm, we run the truncated power iteration algorithm to find a new set of candidate support. We add the candidate support submatrix to the unknown matrix Z, and we solve this problem by alternately minimizing this loss on each of the matrices Aij, where we fix the values of other Aijs. So we fix the other coordinates, we minimize towards one direction, and then we repeat several times this minimization. This gives us a solver to the problem, and we know that under some conditions it's going to converge pretty fast, and numerically it seems to work. And we did some comparisons with Sparse PCA that I'm going to show you at the end, where this optimization algorithm leads to better results than the standard Sparse PCA heuristics that exist. And the point about this algorithm is that, so even though the problem is NP-hard, and we wrote a convex relaxation of the NP-hard problem, which again leads to an NP-hard problem, still by using the convex geometry of the problem, we wrote an algorithmic routine that leads us to an algorithm which converges fast in cases where n is small, and we are using the properties of the convex problem, like the KKT conditions, in order to provide guarantees on the problem. So we did a set of numerical experiments which helped us verify that our theoretical finding was correct. So basically, we computed, we denoised we built a matrix which is okay. First of all, here in this plot, it's one atom plus a small noise matrix, and we denoise this using our algorithm. And we did the same thing by denoising using the trace norm and the L1 norm. The trace norm, and here in this plot, I plotted the value of the mean square error in terms of various values of k. So what we see is a constant scaling of the trace norm error in terms of k. And this was expected because the trace norm's statistical dimension doesn't depend on k, whereas the L1 norm statistical dimension depends on k, and our norm's statistical dimension also depends on k. And the dependence is quadratic in terms of the L1 norm, as I said, in terms of k, whereas the dependence of our norm statistical dimension in k is linear. And here we are reading these in these log-log plots. By looking at the slope of the red and the blue curves, the red curve is twice less sloping than the blue one is. We also use these numerical simulations to verify the intuition that we had about the statistical dimension at larger ranks. So we were expecting that when the KQ rank of a matrix gets larger, the statistical dimension should evolve linearly or sublinearly with the KQ rank. And we were not able to prove it mathematically because the computations already got very long for a rank 1 atom. But numerically, it seems to be true. So we conjecture that it is true for matrices of rank larger than 1. And the other thing that we verified is that when the several blocks of the unknown overlap, it gets harder to estimate them. And in terms of statistical dimension, the statistical dimension gets larger when the different blocks of the matrix are overlapping. And this is what we observe here by comparing these two experiments where we built atoms of rank, matrices of rank 3 with or without overlapping the atoms to build the truth. And finally, it's the empirical results on the sparse PCA problem, where we see that using an optimization problem, the optimization problem which results from writing the the mean square distance from the empirical covariance plus a penalty term that is our norm, we get more precise predictions of the true covariance matrix compared to if we use the trace norm, L1 norm, or the sequential algorithms that were used previously in order to estimate the covariance matrix using sparse PCA. So as a conclusion of the whole talk, I discussed about how to exploit structural information we may have about the factors when you are doing matrix or tensor factorization, and we quantified the benefits you're getting by using by exploiting those prior knowledge in terms of statistical dimension of the cone that characterizes your set of assumptions in the spiked model, or by using the sparsity of the vectors in the sparse PCA case. We build algorithmic routines. We discussed algorithms that converge fastly in case we know a good projection onto the cone C, and that are that are proved to converge to a good local maximum of the optimization problem in case we start from a good initialization point and we have high signal to noise ratio. And we saw two generalizations of the rank 1 spiked model. First, to the case of tensors of order larger than 3, where we saw that except if the signal to noise ratio diverges with the dimension of the problem, the estimation gets computationally hard, and we conjecture that between the value mu k that we exhibited, which was asymptotically square root of k log k, and a term which is of order of n to the k minus 2 over 4, this computation is intractable, even though statistically we know that the maximum likelihood estimates the vector correctly. And finally, I discussed how to extend the problems to rank larger than 1 by using these atomic norms, and we discussed some algorithmic routines that are associated to these atomic norms. So I guess we have a bit of time, and I'm happy to get questions and discussions.